All right. So, last time we were kind of finishing off talking about sort of the set of pretty well trodden reinforcement learning methods such as Monte Carlo, TD, and we're getting into deep Q learning as well. So, this week we're going to sort of finish off the reinforcement learning section of the course and talk a little bit more about deep reinforcement learning and some of the more interesting directions things are going right now. Some of the papers that we'll talk about in this particular lecture are pretty recent, so hopefully this will give you a flavor for what's going on kind of today, but keep in mind, right, these things get obsolete pretty quickly. This field is changing quite rapidly, so keep that in mind as we go through this. This lecture is going to start to kind of veer off in the direction of the rest of the lectures, which will just talk about different papers and results. So it'll be a lot less theory heavy. And I also kind of want to call out that any one of the papers that we're talking about, for the most part, especially in this lecture and the lectures after, would make for really good projects, either in the context of this course or just in general for you to go and try some of these state-of-the-art methods. So just wanted to kind of bring attention to that because often when you're getting into machine learning, reinforcement learning, or any of these things that we're talking about this course, uh, some of the best ways to really learn it and grok it and understand it deeply is to go out and build these things. So just wanted to encourage that, especially with regards to the context of this course, which we're giving in the IGM department at RIT, right? Applying deep learning to game development. Well, it's pretty easy to see how reinforcement learning is directly applicable to game development, both in terms of building agents that can play the game as AI, reinforcing different game mechanics. There's a lot of really interesting things that can be done with RL, and we're just scratching the surface with regards to deep learning and applied to game and entertainment or interactive type of applications. So you'll see a lot of those things actually here. We talk about animation or physics-based animation. For example, as we'll see in this lecture, certain techniques have been used to actually train ragdolls to do things. So we're used to sort of ragdoll physics when you shoot an opponent in a game and all of a sudden they lose all the animation, they just turn into a ragdoll that kind of flops around. Well, imagine that physics-based entity now being able to move around based on the physics of the actual thing. So there's some really cool um, projects and papers on these subjects. So definitely encourage, even outside of the context of this lecture, for you all to go out and look for these different things, which I'll kind of talk about. So let's get started. First, let's kind of review last week. I'll move my disembodied self here, just so I'm not in the way of all the equations. But as we talked about, right, recall that if we know the model, again, we're in this context of a MDP, a Markov decision process. We have an agent that provides an action to an environment in which in return you receive a reward signal and a new state, given that you're setting an initial state. So if we know what the transition model of a given MDP is, then we could just iterate the value against this sort of state action value function or just the value function directly, which then implicitly defines a policy that we can take. Essentially, we choose the action that is the maximum action that maximizes the reward for a particular state. And as we saw with the Bellman backup and the Bellman equations with dynamic programming, we could essentially find the optimal policy in this way. So just wanted to kind of remind you, because some of the techniques we'll talk about in this lecture are going to kind of talk about model based. So I really want to double tap this, but also go through the entire set of techniques because we'll be talking about all of them, but now in the sort of deep learning, the deep learning context. So as we saw in the previous lectures, right, we can essentially iterate our value function or our state action value function, and then we get an implicit policy from that. So the next step up, like say we don't have the model of the world, we can utilize Monte Carlo methods, and Monte Carlo essentially requires an episodic MDP, meaning we have to have a termination state and we have to have complete end-to-end trajectories. We don't know the transition model, but we have that requirement. And here what we're doing is we're essentially running our policy and sampling our environment And there are a variety of different ways that we can update our Q function or our value function, be it first visit, every visit, or this incremental approach, which is kind of in between. So again, just as a refresh on that. Then we have something that allows us to combine the dynamic programming and the Monte Carlo approaches with what's called temporal difference methods. And what we do is we actually have a target. We have a value function target that we then just sort of incrementally approach. And we no longer need an episodic environment. We could do this either on policy in the context of SARSA, where we're using our current policy to set that target, or we're doing off policy, which is also called Q learning, where we're using a different policy, meaning we're actually using, again, that implicit policy as defined by the state action function. So very, very effective. This allows us to, at every incremental iteration of this technique, to arrive at a slightly better value function. And what we're really doing is the dynamic programming, the Bellman backup here, and so we're actually guaranteed convergence under some assumptions. So the next thing that we talked about last week was policy gradient. So assuming we have some kind of policy that we can take the derivative of, we actually showed that we can then calculate a cost, an expected cost over the distribution of states that we see under a respective policy, and that distribution multiplied by the value function of those states gives us a value. And if we take the derivative of the gradient of this cost function, ipso facto or whatever, you end up with the gradient of the policy, which is really, really a powerful idea, because now if we can sort of define our policy by way of a set of parameters, we can now improve our agent's behavior simply by taking the gradient of our policy respective to this cost, just the policy. And given that we do that against this sort of baseline, we can use a baseline, we can just use the Q function that we're updating tabularly or otherwise, we'll eventually get to a better and better policy. So this is a very cool idea. In the last week, I think we already kind of talked about some of these deep reinforcement learning concepts. For example, policy gradient, we're already getting and scratching the surface here because we have a policy that we have to take the gradient of. Granted, it could be a combination of linear features, it's not a deep network and what have you, right? But we're ultimately approximating some very complex function, and that function being a policy, which, given taking a state input, outputs a action that we take that we then plug into our agent. And so, to kind of double down on this, right, the policy gradient is literally just that. And often what we do is we will take the state and encode it further by some kind of function. Say we have a state which is a very high dimensional image, or we want to maybe encode that into a simpler representation. Sometimes our state are multiple frames, and we actually want to append the previous and next frame in our from our environment, such that our agent or policy can take into consideration what has just happened or what is about to happen, and or what information we have available to us. Remember, again, in policy gradients, often we're using a replay buffer, so we're not learning on the data from this particular thing, but rather for what happened in the past. So this is a thing. Something I wanted to note here, right on the top right image here, we have a example of a policy gradient algorithm where we're taking in inputs from a robotic sort of assemblage and then deciding how to control and how to update that assemblage. And this is actually from the TRPO paper, what's called Trusted Region Policy Optimization paper. This still uses policy gradients, but in the policy gradient, one kind of notable thing here, if you start to talk about it in the deep learning context, is the gradient that we get on the policy defines a direction of ascent, right? We're ultimately doing gradient ascent here, not gradient descent. We're trying to optimize a value, right? We're trying to increase and optimize our expected rewards over our horizon. But so how do we know how far to go in that particular direction? And so, you can sort of experiment with that hyperparameter of the learning rate. And the learning rate in this case is not learning on a classification trying to optimizing a particular function, but rather how much are we nudging our policy in a particular direction. You can kind of imagine this intuitively. Well, what if we push too far and we can have some oscillations and instability, just like we had with supervised learning? If your learning rate's too large, you start to kind of oscillate out of control and outside of your optimum. Whereas if the learning rate's too small, you take a very, very long time to get there, and so you kind of want to get it just right. And so I won't get into too much depth here, but TRPO, or Trusted Region Policy Optimization, tries to sort of analytically determine what that is. But that's a little bit outside of the context of this, but if that's interesting to anyone, either take a look at the paper or let me know, and I can put it together in another lecture specifically on TRPO or really on policy optimization. There's a number of other algorithms in that direction, like proximal policy optimization and TRPO and so on. So this subject does get quite deep, but this lecture is not going to be about that so much. It's going to be more about how can we leverage deep learning for these things. But just wanted to kind of put a note there for anyone who's interested in exploring that further. We also saw deep Q learning, right? So in this case, instead of a policy, we're talking about the Q network, and we're approximating this Q function as a network, as a deep neural network. Here we also see state encoding is a very common thing. In this case, we take in a state and we're optimizing this Q function, and then we have this implicit policy that we take based on the maximization of that Q function. So pretty cool. Then we've also seen kind of the combination of these two, and we didn't talk specifically about how actor-critic is a deep network, is a deep algorithm, but in DDPG, essentially we combine these two things, and we have one network that approximates the policy and another network that approximates the Q function, and you can kind of see the DDPG algorithm here that we can kind of go through. So we start off and we initialize a critic network and an actor network. And the actor network, by the way, uses this designation mu. I can't think of the word I'm trying to think of here, but anyways, we have these weights that parameterize both the Q network theta Q and theta mu, which parameterize the policy or the actor network. And then we initialize these sort of clone networks. Remember, this is because for example, in DQN, we had to have a target network and we had to ensure some kind of stationary distribution on that target. Otherwise, we would have oscillation and with kind of unbound behaviors, which, by the way, this is a different area of research as well. So cool. So now we initialize a replay buffer R, so we just save our memory, and we initialize a random process. This N here is the Gaussian for action exploration. We receive an initial observation state S1, so we're ready to go. Now we select an action, and we add to it some kind of random process. So this is kind of a Gaussian that they've added just to encourage some amount of noise on the policy. And this is sort of we haven't talked about it too much in the context of reinforcement learning, but trying to encourage exploration, right? We've seen this already in the sort of greedy case, right? So 95% of the time you take the action dictated to you by the policy, but 5% of the time you take some random action just you pull out of a hat. And so this is sort of their version of greedy, but for a policy gradient case, because how do you choose greedy on a gradient on a network based policy? Then we execute that action that we've received from our kind of combined stochastic policy slightly, and we get a reward and a new state. We save all those as a tuple inside of our experience buffer, and now we randomly sample our experience buffer n number of times. This is our mini batch of training examples that will then run our Q learning on. And so now we have updates for our Q learning. We update our critic by this update rule. Right? We have our target, and then we subtract our target from our current from our current network, and the target is defined by the clone. So again, this is where you see that stationary distribution, and this just becomes a supervised learning task. And then we also update our actor policy based on the gradient of the policy, right? So just this this nabla theta mu times mu, right? This whole thing. And once we have these updates, we now update our two networks respectively. And this is just an exponential weighting moving average. The idea being, so I guess it looks like they're adding a little bit of momentum here. So instead of completely switching, we're adding just a little bit. And this is some form of this temperature parameter allows you to really control how quickly we're updating our stationary targets versus, if the temperature is 1, then every iteration we're updating it. If the temperature is 0, we're never updating it. So if it's somewhere in between, we're kind of slowly, incrementally, or it's almost like a momentum if you can kind of read it that way. So DGPG is a sort of deep version of actor-critic, as we've seen before. This image on top kind of just shows you a sort of example architecture of this, right? We take these images, we run them through these various networks. And actually, this is also something that is interesting to kind of point out. You can share the network between the two, actor and critic. And what you do here is this last layer of this network may be some kind of embedding layer, right? So maybe it's 1024. It's like a flat, ML, like a perceptron type of a fully connected layer, and then you can add layers that sort of split there and go to your actor or to your critic networks. So this is again this example of parameter sharing that we've seen in a variety of different cases before, and also what you could also consider a joint loss, right? So now this underlying network with convolutional pooling layers and so on is being updated not just by the actor but also by the critic simultaneously, which is a very interesting idea. So when we're talking about this update on the parameters down here, and we're switching, while the loss is being applied to the entire network, the actual update rule is applied only to these sort of last layers, or this sort of attached thing. In a sort of funny way, you can sort of look at this front end as a very complex state encoding, and then these actor and critic networks are still individual networks, but the state encoding gets updated. This learned state encoding gets updated by either network, which is a very powerful idea. We'll see this more, by the way, in the next few lectures where we'll talk about neural rendering, for example, and you see this in things like neural radiance fields, where you have multiple tasks. Well, it's not really multiple, but you have these sort of multiple views into a particular network. And the network's quite simple, but because of that sharing of parameters across a variety of different things, you end up getting a really, really complex function learned simply by construction. So this is something, at least my personal interest is in this, and is you see a lot of this very effective inducing a bias in a particular algorithm by way of construction. So the networks themselves are quite simple, maybe like an MLP or something, but the way we design the algorithm ultimately inducing this really, really deep bias into the algorithm, and resulting in things that can do really, really crazy approximations of stuff, still with a very simplistic type of set of functions, like approximation functions. Cool. So moving on, now we're going to get into model-based reinforcement learning. And so I don't know if you recall, I'll just move myself a bit. If you recall, right, we've talked about model-based reinforcement learning in kind of a negative way before, because we've said, well, why would we ever do this? Well, if we know the model, great, we can just treat it as a planning task, because we can just sort of run the dice on all the different ways we could go from here, right? Even things like Monte Carlo tree search, for example. But the world is very, very complex. It's almost intractably complex, right? So for very, very contrived examples like a 4x4 grid or something, perhaps we can learn the model there. But just by counting, or perhaps we know the model in the case of like a game, say we're playing Go or something, we know what the model might be. But in realistic scenarios, we would never know the model. How would we know what's the transition probability of taking a step outside? It's a very complex set of things that happen just for me to take a step out into the real world. But one thing that we've sort of seen as almost a theme here in this course, right, is that machine learning, if anything, is giving us a set of tools to learn arbitrarily complex functions that we know very limited things about, to an arbitrarily small degree of, or a large degree of accuracy. And so a deep approach to reinforcement learning actually provides us a path here that say we can have an environment, we can learn an approximated model of that environment, and then use that approximated model to start to predict or to do all of everything that we've been doing so far, but on this sort of predicted model. And why might that be better than just testing the world? Well, we'll talk about that in the next slide. But first, I wanted to kind of say this following list of things is very not exhaustive, so I'm kind of jumping around in timeline as a little bit as well, as you'll see. I'll kind of call that out. And also, really, and this is maybe a bit of hand waving, so don't hold me to this, but model-based methods haven't been as popular. More you see a lot more research around model-free methods, and I think this is my personal opinion. I think one of the reasons is because up until deep learning and sort of neural networks, it wasn't so trivial to do model-based stuff that actually worked, and so more attention was paid to things like model-free. um, but then with AlexNet and ImageNet and all that in 2012, it's only been 8 9 years. It's a relatively short amount of time. We're seeing more and more of these results, and actually in the last few years, as we'll see in this couple of next slides, you'll see some really fundamental results have come out. So it's a pretty exciting time to be looking at this stuff. So with that, what does learning a model of the world even mean? So in a tabular setting, learning a model of the world is just counting, right? We can just sort of say, how many times have I seen this state? And with Monte Carlo methods, we could essentially just compile that into a set of transition probabilities and use that. And so once we have a model of the world, now we can just use dynamic programming. Now we could just sort of say, okay, let me iterate on this policy, let me iterate on this value function, and so on. Sometimes we have a model of the world because we know what the world's doing, like a game, right? Like a game of chess or a game of Go, where the state space is finite, right? Or at least predictable or defined. It might be very large, but it's still something that we can create things like game trees around, and then we can just sort of use something like Monte Carlo tree search, where we're sort of sampling this thing. That's a different subject. I'm not going to go too much into Monte Carlo tree search in this lecture or in this course, but it's a pretty powerful technique that was used actually in AlphaGo. Was the kind of backbone of that entire algorithm. Although the next one, Alpha whatever, the thing that beat AlphaGo, then got rid of Monte Carlo tree search and was full end-to-end deep learning. I believe. I think so. I'm not 100% sure, but yeah, we're not talking about that here. So watch the documentary. But more generally, if we can have a model of the world, we can just sort of run this policy against it, and now we can update this respective dynamics model. This has just become supervised learning, and then we can use that model to optimize our policy and sample the world again, and go on and so forth, right? And so this kind of diagram on the right here kind of runs us through this, right? We run a base policy and we collect a set of tuples that we put into our replay buffer. We then learn a dynamics model, which is just a supervised learning function, right? Essentially, we have our state transitions. We have a function that approximates what those transitions, like what that state should be given a particular, set of actions and so on. And we just backpropagate through this function. This is just a neural network, right? And then we have this. This also backprops all the way into the policy, because ultimately the policy is the thing that was used to generate those state action pairs. And great, so now we're done, and we now run this new policy that we've received from this backpropagation into our real world, into the environment. We get a new set of tuples, and we rinse and repeat. And we just do this forever. The idea being here that we have this sort of policy that gives us these tuples against the real world, right? We're now learning an error against what we predicted, what our model predicts, and what we actually have seen. And that error, because the tuples that we've seen is defined by the model, by the policy, right? Both get error and get updated. It's almost like this, as you can see at the top here, right? if you go all the way to the right here, we see the new state is a function. Our predicted new state is a function of the our model, our learned model, and that goes back and updates our policy, and then so on and so forth. So it's pretty cool if we can do this. Now, why would this be a good idea? I mean, why doesn't everybody do this? Well, first of all, this I think is really unlocked by deep learning, and this isn't always a good idea, right? If our world is quite simple, if it's a tabular setting, this is kind of a waste of time because we could just count and we get the exact same results. But say our environment's very large, high dimensional, right? Like say it's a video game, or say it's a robotic assembly trying to do something really complex in a simulator, right? Sometimes sampling this learned model, which could be defined by us, is much, much easier and faster than sampling our environment. Both in terms of time, say it's a physical environment, and it takes some amount of time to, play an action and get and learn these things. But also, say it's a very high cost environment, meaning we have a very, very like what's called fast reinforcement learning scenario. And by fast, meaning you want to learn like the right thing to do quickly, because if you do the wrong thing, maybe people die or something like that. For example, in a medical scenario, you want to learn what the right drug to provide is, which by the way is not this problem, because that's more of a multi-armed bandit kind of situation. But say you have a situation that is very, very high risk or high cost. When you fail, well, a learned model or using a simulator or something like that in the loop may be much easier to do than to actually test our environment directly, because and then we have a high cost of making the wrong mistake or making the wrong decision, and things like that. And so there's like this is sort of like a skinning a cat thing. There's a lot of ways to do it, and if your problem requires it, you'll know. But to me, this is kind of philosophically very interesting, and I think more aligned with the way that human beings think about the world, right? We're constantly making models and predictions about how things may work, and then we test those predictions by actually acting on them. And so this model-based reinforcement learning to me is a very interesting subject, because this feels like the way that we approach the world, right? For example, thinking through, as we'll see through some of these next slides, how people have approached this problem, right? I can kind of predict what's behind the corner before I turn the corner, and then I know what to do even before I'm there, and that's a very valuable capability. So one of the first results that I'll talk about is Dreamer. Actually, I didn't realize, like, I think this is a pretty new paper actually, and so Dreamer, what it does is it kind of imagines a set of future states, and then it basically makes predictions on those rewards that it may see, and so it has a number of different networks that it's running simultaneously, and it learns this in training, and then can run from that point on things in the future. So I'm not really explaining this particularly well. So let me kind of go through it. And I'm not going to super deep technical depth here on this paper or any of these, so just keep that in mind. But if you'd like me to go into any of these technical papers into depth, let me know in Discord, and I'm happy to do a lecture specifically on a particular paper of interest. So Dreamer leverages both a model for representing the state, so we've seen that already to some degree, a transition model. So now this is our world model, but this is sort of predicting what the next frame would look like, or what's the next state going to look like based on the states that we've seen thus far. And then it also predicts the reward that we may see there. And so you can kind of see these are all the pieces that we need to fit into our reinforcement learning equation, right? And so up here in the top right, you can kind of see the first thing that happens is we have these images, they get encoded into these states. That's the representation model. And then we predict rewards of those states, and then we reconstruct from that the next state that we expect. And so based on that, we can then just run this in forward, and based on these actions that we take, compute the most optimal action to take based on the representation, transition, and reward models that we've learned, essentially. And this is kind of creepy that it works so well, because really what we're doing is we're doing this all in these imagined latents. And so we're taking the state and kind of squishing it down into a lower dimensional representation. We're taking the transition model and again, squishing it down into a lower, dimensional representation. And then same thing with the reward, right? And using these models to then predict, well, what state will I be in? What's the reward of that state? And also, and we're using the representation model to do this, which we'll see again very soon, this representation model idea. So this is not a new idea, actually, because this came out a little bit later. But regardless, now that we have these, we can just sort of predict what to do next based on the actions that, the transition model and the reward model predict, right? Because if I have my current state, my current observation, I plug it into my representation model, it pops out. Then I plug that into my transition reward model, and I can then tell you what's the best action to take, because I have a variety of different states that I can take, and then I can decide what the best action to take is, right? For talking specifically here, right? The transition model is going to predict the next state based on the previous state and the action taken. And once I do that, then I get a new state, and I can plug that into my reward. And so if I have, say, a finite number of actions, I can just plug in all my different actions, figure out which one, and again, we're just back to argmax of the Q function, right? Because that's exactly what we're doing, right? We have a state and the variety of different Q functions. But again, I'm talking about this very hand wavy and high level. But if you'd like me to go deeper on this particular paper in the technical depth, I'm happy to pop it open and do so, because we're just going to go through a bunch of papers in this lecture. This paper, this approach is to me, is very cool. It's a little bit kind of spiritually different than the one that we just saw. And it's a little bit older, I think, which is surprising to me. But in this case, what we're doing is actually this A3C agent. So A3C, just really quickly to cover, is an actor-critic algorithm. We haven't talked about it. It was designed a little bit more to take leverage parallelization, because as we've seen, reinforcement learning is a very data inefficient process, right? You need a lot of data. You need to run this for a long time before you figure out these policies. It works, but it can take a very long time. And so A3C was an approach to kind of do this in a more distributed way, and also introduces this entropy regularization. So the idea being here, and I'm really glossing over this quickly, but the idea being that we want to encourage our policy to have high entropy, which means that we have some kind of sparsity or some kind of spread in our policy, meaning a policy that chooses the same action every single time has no entropy, right? Because we know exactly what action we're going to take. And whereas a policy that takes a random action has the maximum entropy that it can have. So we want somewhere in between there, right? We don't want to be acting like crazy and taking random things, but we want to encourage it to be more random. We want to encourage it to explore the space, the action space, and that's what this entropy regularizer does very, very quickly. And so this top loss here is just the A3C, right? So this is the value reward, the policy loss, these are just the Q learning and the actor critic, right? The Q learning and the policy gradient losses, and then minus this entropy regularizer. So the intuition with Unreal is that, okay, well, we have this actor critic thing, but sometimes the reward signal is very sparse. Sometimes it takes a very long time to find the golden nugget in our environment. And so what can we do about that? And so Unreal introduces the idea of auxiliary tasks, meaning maybe we don't only define our loss or our value based on the reward function. Maybe we can define other things that can value. So for example, down here in the reward, the loss for Unreal, we have the A3C loss defined up here. Then we have this thing called the value replay loss. The value replay loss is just encoding a value function replay against our function buffer. And then over here we have this weighted auxiliary control loss, which I'm actually not sure Oh, right, sorry, this one's weird. So this is the Q aux here, which means that what we take is we take our image and we split it up into these sections, and we take the average of those sections. And what we're trying to do is we're trying to change the pixel values in those sections. It's almost like we're just trying to move towards the light. I mean, it sounds silly, and I'm kind of simplifying here, but that's kind of what's happening, right? It's almost like what we're trying to do is we're trying to encourage the network to just move around, to change state, to change the kind of colors of these average sections of the image. And if we can do that, then we can sort of encourage say we're lost, right? Say we can't find the reward, we're stuck in a dark room. Actually, a dark room is a really good example, right? We're in a dark room with a candle. We can't see anything. Well, maybe it's a good idea to just go towards the candle because that at least is doing something. That's some kind of auxiliary task that we can at least do, and then maybe on the way to the candle we'll find a trap door and then go down the stairs. And then finally, we have this reward prediction, which is just a network similar to what is being done in Dreamer, right? We're trying to predict a reward for a particular for a set of states, and if we do that, then we give ourselves a cookie. So it's almost like a anticipatory type of reward. You can go into the depth. They tried a bunch of different things in the paper, and you can kind of read the paper as I linked it here. But what's really kind of the intuition here is that perhaps the reward signal is not the only signal we should follow. And I think anybody who's played a video game can kind of appreciate this, right? Sometimes you're playing a game, you know what the point is. You start to create these little mini games for yourself, right? Or say you're playing a game and it's really hard. Something's really hard. Like RPGs are pretty notorious for this, right? Where you're not quite leveled up to do a thing you want to do, so you start to do random things throughout the world and you explore and what have you, and eventually you level up to the level you need to be to go and beat the boss. So this is sort of that in a reinforcement learning type of context, and this is pretty effective as well. So it's worked in a variety of different environments, and again, I recommend checking out the paper to see what those are. But yeah, so this brings us to world models, and this is also a relatively recent finding, like a year or two, maybe. It's a little bit older, I suppose. But here, it starts to get really interesting, where we're starting to try to disentangle the state of the world, and then use that disentangled representation to then decide what to do. In a way, this is similar to Dreamer as well, because that's sort of what's happening here, right? We're taking the current states, we're learning some representation, we're plugging it into these other networks, but here it's a little bit more explicitly defined as such. And so what we do is we take, our state, we use a VAE, as we talked about. The VAE really encourages that Z latent to be disentangled, and then now we can predict the future. And the way we can predict the future is if we do this enough times and we run it in an RNN type of fashion, right? The next time we run it would mean that we should expect the next state as well. And so we can do this in this sort of RNN type of structure. And now we have this Z latent for our current state, but also this Z latent for our next state. And what that means is we can then sort of predict the future, and we can also now make control decisions based on a lower dimensional representation of the world as learned by this sort of disentangled VAE. The VAE gives us a disentangled representation. So I'm kind of glossing over a lot of detail here of how it actually makes a decision of what to do, right? That's part of the controller and what you're doing with these future states. But I think what's really, really important about this, right, is that now we have some kind of system where we can predict the future and we can try different actions. We can actually say, okay, well, if I do this, this might happen. If I do this, this might happen. And we can do that for all the different actions. And not only can we do that for all the different actions, we can do that for all the different actions and then the resulting states and all of those. And so we can start to do almost tree search based on our own model representation, or our own model, learned model of the world. And so kind of I want to just go through this is from the talk that the authors gave on this, right? And so at every step, right, the agent gets an observation. So this is an image or what have you, like they're doing this on the doom ducking environment. The vision model that they have encodes that state into a lower representation latent, right? That memory model, the RNN, now integrates that and creates a hidden state that it kind of passes on and on and on and so forth, because now it can sort of predict the next state, and then a controller then can decide the action. So now this controller, based on the hidden state and the Z, the representation, can now predict what action to take. But you can kind of see in this image up here, right, where we can actually keep going. We can turn off the Z. We can just keep going, right, and take this Z and plug it into the next one, and that way we can actually have a prediction of what our next model, like we could actually just run this in the forward, and so on. So just some ideas. Again, I'm glossing over a lot of details of how that actually works in practice and so on, but you can kind of see some really, really interesting results here that now we're starting to really model the world. The last thing I want to talk about here, and this is kind of a bit of a left turn. It's not quite reinforcement learning, but you can see a lot of these really similar ideas here, are generative query networks. And so generative query networks kind of are a little bit less RL centric, but in a way, this is really one of those examples of I want to know what's around the corner. I can have a set of observations, and now I can basically say, based on these observations, this is what going through this environment might look like. So this is a little bit more on the neural rendering side, but you can kind of see all of these RL and agent type of ideas here, where we are given a certain set of observations. We use those observations to then create a representation of the scene. That scene is then stuck into this sort of generation network, which uses, in this case, it's using an RNN to kind of iteratively generate the environment. But it looks very similar, right, to the Dreamer architecture, ultimately. And so you can kind of see where things start to sort of merge between the two, because I think generative query networks came from more of intuition, more of a desire for RL, right? I want to understand an environment in a spatial way, but it's quite cool and it works quite well. Although some of this network happens to be really big. Another thing that generative query networks do, and this is again outside of the context of RL, it allows you to do scene arithmetic. So we learn this representation, and now we can imagine environments that don't even exist by subtracting different environments against each other and things like that. But that's a little bit beyond the scope of this. If anyone is interested in this particular paper, I have a lot of depth in this one because I implemented it recently, and I'm happy to talk to it more. So let me know if you'd like to have another lecture on that particular paper. It's a good one. Okay, so next subject. I wanted to talk a little bit about imitation learning, because I think this one's it's an important thing we haven't really talked about in the RL section, but imitation learning is a sort of subset of RL, but it's kind of a weird one because it's a little bit of a different approach to these things. So say we have a set of expert trajectories. So for example, we have a bunch of people who played our video game, and we recorded the input that they put in, and then we record like the video or the output or the state or whatever we want of that thing. So for example, in the top right, we have this video of the Minecraft ML agent. This is from like a competition where they essentially give you these trajectories for like 60 million hours of Minecraft play, and it's a competition to see who can write an agent that's able to essentially mine a diamond fastest. So that's the competition. It's fun stuff. But so say we have these trajectories, could we, in theory, find a way to learn something from this, right, without even having access to the environment and there's a variety of different kind of topologies here. So imitation learning is all about trying to imitate some aspect of the RL problem given these expert trajectories. So in this case, we know we have a set of trajectories from an expert, meaning it's a human player or it's someone who knows what they're doing. We're trying to imitate this behavior. And there's a kind of two flavors of imitation learning, or two main flavors, although I might be a little bit off. There's a kind of a third one, but it's sort of in between the two. So I'll just talk about two of them. There's what's called behavior cloning. And behavior cloning really kind of just tries to learn a policy as a supervised task against these, set of trajectories. It's almost just like, hey, what's the next, action we should take based on what, these trajectories are saying. It's sort of limited in success because you can imagine how varied a set of actions could be in a high dimensional type of environment. This would work really well for, say, grid world and for really simplistic kind of contrived scenarios. But for, say, Minecraft, right, how many billions of different ways are there to, just play Minecraft for the first 10 seconds? It's a very, very unbound type of scenario. Um, so it's to limited effect behavioral cloning. Also, there's kind of this sub version of this like direct policy learning, and in this case, what we can do is we can say, well, I think I should take this action, but hey, expert, hey, external expert, tell me what to do. What do you think? And this can be done, for example, when you're off the path here. This is sort of demonstrated here. Say we have the trajectory, we're like line following, but then we're off the line and we don't have any data that tells us what to do in this scenario, and we keep going and we crash, right? So this is a good example of what expert learning is doing, because here, if we can kind of come up with a uncertainty threshold of like, hey, I'm over here, I don't have data, I don't know what I should do. Hey, expert, tell me what to do, and they can correct me, right? And maybe I can learn from that as well. So this is also what's called human in the loop. So if you come around and you hear about reinforcement learning, human in the loop, they're often talking about direct policy learning. And then inverse RL is the other kind of side of imitation learning, where now we're using these state action pairs to try to learn the underlying reward signal. If we can learn the reward, then we just insert our reinforcement learning algorithm of choice. So on the right here, we kind of have the two examples, right? For behavior cloning, we collect these trajectories, expert trajectories. We then just treat them as state action pairs, and then we learn a policy using a supervised learning algorithm, right? This is just quite, vanilla. On the bottom, the inverse learning, right? We have a bunch of expert demonstrations. We tried to learn this reward function, and again, because our trajectories provide us with the reward that we've gotten, and again, it's just a supervised learning thing, and then we kind of compare and then we use that reward function to then learn a policy using some RL algorithm, and we compare the policy that we got with the expert policy, and we eventually stop if we reach some kind of convergence or some kind of threshold that we're happy with. So this is sort of like the very quick nutshell lightning introduction to imitation learning. But the reason I really wanted to bring imitation learning up is because of this technique, these two techniques that I wanted to talk about, called Gale and Veil. And so Gale is to me one of the most kind of exciting things, where you see reinforcement learning and the sort of unsupervised learning sort of colliding head on. Although there's a lot of examples of RL and unsupervised learning that we've talked about already, but in Gale, the idea is we can kind of create a dual problem, right? Where if we can learn the inverse, like the reward function of a given set of expert trajectories, then we can use that to then solve the RL problem. We kind of saw this here. In a way, that's sort of exactly what inverse RL is, right? We learn a reward function, then we kind of go backwards. And so this sort of push and pull is something that Gale essentially maps into a generative adversarial network. And what's kind of cool about this is, if you look at it, this is a kind of simplifying it, but I think is a very, very good way to think about it. In a way, what we're doing, so we have a generator. The generator is generating these trajectories, and then we have a discriminator that tries to determine whether or not this came from an expert or from a fake sample. It's just like GANs that we've seen before, except in this case, instead of like images, we're looking at actions or trajectories. And in a way, the way this works is it's almost like an RL agent that uses the output of the discriminator as a reward function. And that's kind of the cool thing. It's sort of this push and pull. It has some kind of unique dynamics that we want to avoid, and that's a different subject. But ultimately, we have a latent like noise that we're sampling from. This plugs into the generator, just like in any kind of GAN. The discriminator now discriminates between the data sample, like a real sample from an expert trajectory or a policy, and then we determine yes or no, and then this error goes and updates both the discriminator and the generator in kind of an alternating fashion. And again, we see here the the discriminator loss that we would be using. And so it kind of is a very eloquent idea. Um, and also they did a little bit of research, further work here, but let me go through the algorithm because I think this is a good thing to kind of work through. And so we start off with these expert trajectories and this initial policy and discriminator parameters. So these are just networks that are initialized to some arbitrary set of parameters. And now we sample a trajectory from our policy, right? Then we use the discriminator to just update our discriminator parameters with this gradient. And then we take a policy step using TRPO. So I mentioned this before, but TRPO is just sort of a how far do we go in the gradient direction of the policy. And keep in mind we have a policy for the gradient based on this. And so we now can take a KL constrained natural gradient step. And so this, I'm going to gloss over here, but here we see the gradient, the entropy regularizer that we saw before, and essentially just the gradient of the policy based on that before. Yeah, all right. And I haven't really gone too deep technically on this paper, so I apologize, but I'm not exactly sure about the Q function definition here, but ultimately they're using the Q function as defined by the expected value of the discriminator given the state and action pair. And so that's, in a way, kind of what I was saying before, where they're leveraging the discriminator as a kind of reward function, right? Because if you recall, the Q function essentially predicts what our value of taking a particular action is given a state. And so in this case, the way we've defined that is through the discriminator and how well we're doing effectively. So yeah, that's very quick hand wavy explanation of Gale, but it's quite it works quite well. And then led to Veil, which is sort of a very similar idea. In fact, it's exactly the same, except they introduced this explicit KL loss between this encoder of the latent given a particular state and the reward of that latent. And so the idea being that what we want is we want our our this idea of our set of states and rewards and actions to be sort of whoops, let me move over here, a little bit more spread out, and we want to maximize the information between our input to the encoder here. Oh, sorry, between the one second, let me collect myself for just a moment. Okay, sorry. Just took a second. So the big kind of jump with Veil is really around the generator approach. And so with the generator, what we're trying to do is we're trying to kind of squish down our state and our essentially our state down into a latent, and we want that latent to have some kind of information maximization with some kind of prior knowledge. And in this case, we're just doing this KL loss between in this case, in the Veil case, we're doing it between the reward of that function and the encoder of that Z given that state. And in this case, the reward, what we're saying is we're going to model it as some kind of Gaussian or something. So this just becomes that traditional KL divergence loss from a VAE. And then we have this threshold that is just a hyperparameter. And so what we're doing here is we're just encouraging more, I think, a more continuous prior in this latent, not continuous prior, but a more spread out, a more disentangled way to we're encouraging the generator to generate samples that essentially cover a more general space in its distribution, and we do that by way of VAE. And so ultimately, if you look at the Gale example, right, and the Veil, it's essentially the same except for this KL divergence loss, which just is almost like just like in a VAE is almost like a regularizer. It's just encouraging that this disentanglement of this representation, because ultimately this generator is still taking it's encoding the output of a generator, as in the case of Gale, it's encoding it and then it's decoding it back and then providing that as an output. I think this DZ is incorrect. It should be DX because it's or DX tilde or whatever. But yeah, and this results in like slightly more superior results than in Gale, but it can do some really cool stuff. So like for example, in the top right, you can see some of the examples. They can teach an agent. This is a ragdoll agent, meaning it's a physics-based movement, ragdoll to do backflips and cartwheels and run and dance and do some really amazing things. And if you compare this to Gale, because Gale does this too, it's just less erratic. It's more even and kind of smooth. That's what I was meaning by it's more smooth. What they're doing is they're really encouraging the exploration of the space of the learned policy. This is actually really, I think, important. And the reason I'm really kind of perseverating on this with with this class is imitation learning maybe isn't so useful for certain things like maybe like we actually had a student last semester who used imitation learning to train an agent that then you could play as an AI, and so that was really cool. It got pretty far. So imitation learning is useful there to train AIs to do things, certain things. But in the case of the top right, this is just using mocap data or motion capture data as the ground truth, and so it's imitating a human being. It's saying, okay, here's a bunch of animations that we captured from people in a motion capture studio, and now, hey, Ragdoll, learn how to do these complex motions. And using imitation learning, it's able to learn how to balance, how to move, how to do a cartwheel, how to run around. So you can kind of imagine the application of this to a physics-based character in a game that is bumping into people and to trying to do these things. Because what's really cool about this imitation learning thing is you can create multiple different policies. You can learn a variety of different policies or generators for a variety of different kinds of behaviors. Right? So now I'm running, now I'm walking, now I'm opening a door, and so on and so forth. So some really interesting sort of future directions to explore here. So finally, I wanted to sort of talk about this. Oops. Okay. Looks like I doubled up on this particular slide. Sorry. So last but not least, I wanted to talk about GameGAN. And GameGAN is a really interesting example because it sort of leverages a lot of the different things that we've talked about in this class so far, be it a GAN, but we haven't talked about neural Turing machines or anything like that. But what it's doing is it's creating an end-to-end system that could essentially learn a game. And there's a lot of RL concepts in here, and there's a lot of unsupervised concepts in here. But what's happening, and so it has this sort of LSTM-based recurrent neural network, and that's the dynamics engine. If you can imagine, the dynamics engine is taking an action from the user, it's taking in this memory from the previous memory input, and so on, and an image, the last frame, and it's trying to predict what the next state of the system is. So this is very similar to the world models that we've seen. Now, what's interesting here is that there's no like concept of an agent, right? But you can see in this learned version of Pac-Man, right? It's actually, like learning that there's these, enemies running around and so on, and that you're, eating these little Pac-Man tokens or what have you, and even it can learn that when you eat like a cherry, all of the baddies have to turn red and so on. It's quite amazing how far this game went, how this technique went to learn the entire end-to-end dynamics of a game. And so there's definitely RL in here. It can be used, and I think a big motivation of the paper and the project was for again reinforcement learning or just generally learning intelligence in this context. And so the components of the system are this dynamics engine, which is this, again, like I said, LSTM-based RNN, and it just continuously updates this future state. That future state is conditioned on the memory, on the action, on some random noise, and also the previous image that we've generated. So our own previous image is used. And so then we have this concept of this memory module, and we haven't talked about neural Turing machines yet, but neural Turing machines are really interesting. I highly recommend you guys check them out on your own. It's basically turning the operations of a computer into a differentiable set of operations so that then you can learn computing operations. This is kind of like a creepy idea in a way. So imagine training a network against, a sorting algorithm on 10 or 20 items, but now you have an algorithm that's learned an approximated version of that algorithm, and you can run that algorithm on thousands or millions of items. This is a interest of mine, and I won't go too deep on it because I haven't gone too far down that road myself. There's some really interesting ideas around neural Turing machines and neural GPUs, in that if you can learn an algorithm to an approximate degree, in theory, you can bound the the compute profile of that algorithm, but then scale it up to whatever scale you want, which is an interesting idea, right? Imagine writing a sorting algorithm that has a finite time complexity, uh, but as a result of that has some kind of bound or expected error. So it's like I'm going to sort these billion of items, but it's only going to take me this amount of time every time, but there's some error that's going to be true. Right? It's not going to be perfectly sorted, but it'll be like maybe just enough. So, anyways, the reason they're using a neural Turing machine for the memory module here is because in the case of, for example, Pac-Man, right, you have all of this state of which enemies are where, and where are the flashy dots, and where is the strawberry, and what's happening. You need something a lot more strong than an LSTM, and even the context of transformers, which we'll talk about soon, right? How do you update these very, very long-term dependencies, sometimes as long as the entire episode, in this case, an episode being, potentially seconds or minutes or even hours long. So that's a cool idea. And then finally, the rendering engine is based on a GAN. So the idea is it's conditioned on an input hidden state coming out of the dynamics engine. And what this is doing is trying to imagine what the next frame should be based on this hidden state. And the hidden state is, again, conditioned on the action, the previous image, and so on and so forth. And so what's cool about this is that the loss is entirely dictated by whether or not this image looks correct based on the game itself, right? So you're like comparing the image coming out of this network to what should be coming out of the game, and you have this bootstrap period. And if you read the paper, it's really quite interesting to approach here, because you'll play the game, and eventually the game stops inputting into the system, and now you're just playing the game by way of the ML network only. And it's quite amazing that that works at all. But this shows how all of these different components can be put into literally a game. Like this is an ML powered game, a game engine that has been learned from an underlying game. All of the respective components of it. So that's that. That was a bit of a fun lecture through a lot of different sort of reinforcement learning, deep reinforcement learning techniques. And I think that's the end of the RL thing. If there are any particular papers or subjects that I've gone through that you're interested in, please let me know in the Discord, because I think now we're going to move on to some just general ML ideas that are really valuable to know about. For example, we'll talk about transformers, which have really changed the name of the game for, in particular, natural language processing, and are starting to make impacts into generative models in general. And also after that, we'll talk about neural rendering and kind of maybe a wild card lecture after that. But yeah, thanks so much, and see you soon.